Hello everyone, I will present my work on local first-order logic with two data values. So this work was conducted done with Benedikt, Bollig and Arnaud Sangnier. So the context is that we want to study system with which use data. So they are omnipresent. So for example, database, sets of data for learning or distributed and concurrent system. And so we need specification language to describe system with data. So our motivation is we want to specify input-output behavior or distributed algorithm. So the structure, each element we have two data value, and there are no relation whatsoever around on the elements. And the most important is that we want to compare the input value with the output values of the element. So as an example, we look at the consensus problem, which is a very, very well-known problem in distributed computing. So the specification is that we have a cloud of computing unit, and each computing unit will propose a value, and after they all have to agree on one value among the one which has been proposed. So for example, here we have 4 computing units. The first one proposed 1, the second one proposed 2, the third one proposed 3, and the fourth one proposed 1, and they all agree on the data value 2. So for the specification, we will define the first order logic with 2 data value. So first we talk about the structure. So it's parameterized with sigma, a finite set of unary symbols. The structure will be set A, which will be finite. So it's important because we do finite model theory. There are 2 functions f1 and f2, which symbolize the first data value and the second data value. And we have p sigma. It's a set of unary predicates, so we are able to label the element of our structure. So, for example, on the previous slide, we have it's a structure, and we had the leader label. And so for the logic, it's parameterized again with sigma, the unary symbol, and with gamma, the set of binary relation symbols. So formula will be the atomic formula. There are the things that the element x has a unary predicate sigma. How we compare the data value of x and y. So the atomic formula x i g y compare the is data value with the j's. Compare the is data value of x with the j's data value of y. So for example, if I is 1 and j is 2, we compare the input value of x with the output value of y. We can test the equality between elements, and we have FO with the disjunction, the negation, and the quantification over the element. And so the consensus problem can be specified in this logic. As a conjunction, we say first that we have exactly one element x with label leader. So the quantification exactly 1 can be done in first order logic. And the second part is to say that for all element y, there is an element x with a leader label, and that the input value of x is the same as the output value of y. And we'll denote that FO2, the 2 variable fragment. So we look on the satisfiability problem. So we'll denote this as datasets. It's parameterized by f. It's a fragment of the first order logic, and gamma is a set of binary relations. So the inputs is a formula, and the question is either data structure will satisfy phi. So there is already new results on this. So the whole logic is undecidable, even without with just already comparing the inputs and the output with the outputs. But FO2 is decidable. And another related watch is two variable logic on data words. But one key thing in our modelization that is not present in all this work is being able to compare the first data value with the second data value. So to time the indecidability, we want to study we define the local first order logic. So given data structure A, we will define a graph, which we call the data graph, and it depends on the set of binary relation we have, and we'll connect two data in the structure if they are equal. And after, if we focus on the element A, we can look at the balls of different radius around A. Here we look at the radius 1, and we draw this in blue color. And from this we define the one neighborhood of A. It will consist of all elements having some blue in them. So here specifically it's all the elements having 1 or 2 as data value inside them, and the other remaining data will put something different, such that they are totally different and we cannot compare them. And notice that we get rid of the element having the data value 3 and 5 because it's not in the ball of radius 1. And so on the syntax side, we add a local formula phi under brackets with exponent 1 to say that it's radius 1 and x to denote the center of the ball. And this formula can only reason about the neighborhood of A. So formally the definition is as follows. So we call airlock FO, so it's a local first order logic with radius R. And so we have this formula psi under brackets. We keep the R to remind of the radius, and we can compare the equality between elements, and after we have a regular FO with quantification over elements, disjunction and negation. And so, for example, the previous formula can be expressed in one log FO. So now we look at the decidability results. So for the radius equal to 1, and with being able to compare the input with the input, the output with the output, and the inputs with the output, so the last relation is which called the diagonal relation, this is decidable. So the proof is we reduce this to the satisfiability problem of first order logic over two variables with no diagonal relation. So there are 4 steps. So the first step is to transform the binary relation into unary relation. The second step is to introduce the concept of well-diagonalized structures. And the third step is to use the two previous steps to get rid of the diagonal relation. And the fourth step is to count this two variable logic. And in this presentation we add a last step resuming all this. So the first step about adding unary predicates. So we look at a structure, and we have a specified element A, and for each element we'll add new unary predicates, which will describe the relation of the data value of the element to the data value of A. And after, for A, we count how many elements they are in relation to A. So for example, the green, when we say that it's when we only have the output value, which is the same as the output value of A, and we only have one element like this. The red one is having the first data value as the same as the first and the second as the second, and we have only one, is namely A, and so on. And so we do this with all the elements, and so this will be efficient to. This will be sufficient to check if a model satisfies a formula, because in the view it's all the information that is needed. In the not the view, in the neighborhood is all the information we need. And if the counting constraint, so we'll modelize counting constraint as a new unary predicate, and we'll say that the counting constraint will correctly describe the model, the structure. We call them the well-typed data structure. So the second step about well-diagonal the structure. So we add diagonal elements. We start from the same structure I as the previous slide, and we add diagonal elements labeled with ed, such that for each data, there is one element labeled with ed having the data as input and respectively as output field. We add predicate eq for the element with the two same value. And so the A and B, we do not need the diagonal relation for this, but if we have a formula satisfying AIB, it's not sure that the EC will be correct, but we can do this by permitting the first data value. And after, to get rid of the diagonal relation, we want to check counting constraints in the extended data structure without using the diagonal relation. So to do so, we use the diagonal element to remove the diagonal relations. So for example, if you want to check whether there exist two elements with the same output value as the input value of A, we check whether for the diagonal element B1, there exist two elements with the same output value as B1. So next, step 4, we want to reduce the counting constraint to FO2, and so to do this, we will count the elements in the intersection. So what we call intersection are sets of elements with the same input and output value. And yeah, so the trick is to add unary predicates to count inside the intersection. After, we add new unary predicate to count the intersections themselves, and we count only up to a certain bound because we are in FO, and we use this new predicate to verify that the counting constraints labeling is correct. And so lastly, we put all this together. So if we have a formula phi and we want to check if it's satisfiable, we build a formula phi cc with counting constraints. We build a formula phi ed in FO2, which ensures the presence of diagonal elements. We build a formula phi wt to ensure that the counting constraints are correctly placed. And so the satisfiability of phi we use to check the satisfiability of the conjunction of the three formula. And this is possible because we already know that checking the satisfiability for FO2 is decidable. So it was the satisfiability part. So now we'll look at the undecidability part. So with radius 3 and no diagonal relation is undecidable, and with radius 2 and just one diagonal relation is undecidable too. And the main tool used is a reduction from the periodic tiling problem. So this problem is as follows. We take as inputs set D, D a finite set of dominoes, and two relations H and V, specifying if the dominoes can be placed adjacency in horizontal or vertically. And the question is there a periodic tiling of the plan with the domino respecting H and V? So the main idea of the reduction is to being able to encode the vertically and horizontal adjacency of the plan inside our structure. So here we draw the plan. Each dot represents an element. In the green zone, it's an element with the same input data value. In the red zone is an element with the same output data value. And the black line represents the diagonal relation. So in conclusion, what we know is that with radius 1 and one diagonal relation is decidable, and with more than radius 1 it's undecidable with one diagonal relation, and for radius 3 it's undecidable. And the perspective is that we want to complete this picture. We want to consider with both diagonal relation with radius 1, and we want to consider the neighborhood, but still with to consider the element outside of the ball in the neighborhood. And the second point is to study the other fragments with quantifier restrictions, and finally to develop approximation for the satisfiability problem. Thanks.